Is Professor Malinnikov, the Vice-Rector of the Moscow State University MIGAIK. His scientific presentation is about the results of the theoretical research of the fractal properties of geodetic lines. So, Professor, please.
Добрый день, уважаемые коллеги. Я хотел бы...
Good afternoon, colleagues. Please don't be afraid or frightened as you look at the title of this presentation. In fact, I'm going to report the results and findings of MIGAIK task force that carried out a project to look into new technology, new methods. But we do realize that if we do not develop fundamental knowledge in this field, it will take us only this far. So this is about fundamental knowledge. The concept of this project was that, that we widely use data from accurate imaging, in particular GLONASS system. We need to be sure that the data that we received from light that carried through thousands, tens of thousands of light kilometers, and this is something that should push us towards fundamental knowledge. If you carry out spectral analysis of fluctuations and spectral density of energy, you will see that there is a number of harmonicas that need to be physically interpreted. It could be ionospheric impact, stratospheric impact, but it's all important for adequate interpretation. So in order to interpret some of such fluctuations, we carried out our project. It is believed that today, in our models of electromagnetic spread, especially where great distances are involved, we must not negate the fact that the concept of empty space is no longer used. We say that we must take into account real properties of the physical vacuum, something that fills in our environment. Yes, indeed, there is no denying that if a body moves by inertia, according to the theory of relativity, this body must move geodetically. We know that, but we must also understand that the science has been advanced, and the concept that was used when this theory was formulated does not work anymore. So, in the next slide, I wanted to show you some of the knowledge which we believe exists at the moment when it comes to the physical vacuum. Without understanding the physical vacuum, a lot of the things that we obtain cannot be interpreted. If we take into account quantum field properties, vacuum has a lot of energy, but it may contradict some of the previous knowledge. Yes, there is a physical substance, physical vacuum, and when we analyze spread of electromagnetic radiation, we need to take this factor into account. Today, we can build several models that suggest that the physical vacuum has a certain structure, certain geometry and topology. We say that the vacuum, physical vacuum, is something that we cannot see. But why? Now let's try to recall here. What can we see? And no matter what we do, we are in a vacuum that we cannot see. We know that the physical vacuum, according to findings of foreign experts, it's a multi-fractal system that has linear and non-linear interlinkages. It's a fairly complicated complex that needs to be taken into account. Today, the physical vacuum is some sort of a space filled with virtual representative pairs. Why do you go so deep into theoretical physics, you might say? Well, you know that these pairs interact with physical particles. If there is interaction in place, it means it affects the trajectory, the path of photon. So this interaction needs to be legislated for. When we talk about the geometry of undisturbed vacuum, we talk about electromagnetic vacuum, we talk about Higgs ocean. You may remember this, which is something that we've been looking for on the collider. And today we talk about the strong vacuum of some condensate, ion condensate. These factors do exist, and they form the essence of the physical vacuum, we argue. But if we use these beliefs, we can apply them in our field, in land survey and geodesy. Geodetic lines are closed. I don't need to prove that. It can be done easily. We verified that, we have proven that, and others did as well. What's important is that this ratio gives us a chance to show a fundamental thing. We can show that the vacuum fluctuations have the property of self-image, self-simulation. In other words, we can say that geodetic lines through which photons travel will also have fractal properties. This is one of the key findings that we arrived at. So we state that if, according to the classical theory in flat environment, photon is a straight light, if we introduce the concept of physical vacuum, we need to talk about fractal properties of the photon. This trajectory is broken down to make it simple. In this situation, you can immediately introduce a different ratio. You can try to describe these trajectories in a slightly different language of fractal geometry. In this situation, you can use something that is known to science and applied science. We can talk about fractal sizes of geodetic lines, and we can talk about other indicators that allow you to describe the proper trajectory. This is an example of varieties of trajectories. An example of varieties of trajectories that can exist depending on the environmental properties. It can be a smooth curve, it can be a meandering curve that goes through cavities, it can be an intermittent curve, and all of that can be described as some sort of fractal model for trajectories. But the question emerges, if we try to introduce this in real terms into science, then in this situation we will have to abstain from using the traditional geometry. It's a different kind of system. So our analysis has shown, if we try to describe these environment, this space that takes into account the properties of the physical vacuum, the best deal will be to take Finsler's space, which is known in mathematics. It is this kind of approach that helps you legislate for physical vacuum characteristics. Legislate for it, and then to create a model for the travel of electromagnetic waves. These are the effects, this is the impact that we believe becomes evident when longer, greater distances are involved, but still they are palpable. So, we can introduce curve factor, segment curvature, and try to formulate some kind of ratio that affects the movement of photon. I did not write down all the formulas, but the general equation has been provided. And finally, speaking about Finsler geometry, what's of importance to us? We can describe and depict the difference between the length of trajectory in the common geometry and in the Finsler geometry. And based on that, we can extract the so-called indicator of frontality, or other fractal properties of Holodorf, which can help us determine the actual length that a photon traveled. So this is the level of theoretical research that MIGAIC working group carried out. In fact, this is only the beginning of our research, something that we tested out, send our feelers into, but it will be continued. The next stage that the university is implementing, that we're piloting, we will try to prove or verify the data that we obtained. These are raw data and information received from GPS, GLONASS, that allow us to examine spectral structure, and we try to validate and substantiate spectral harmonicas existing in this spectra. I may have been too fast, but I tried to present this material to you. Thank you very much for your attention. What's the aim of it? What's the objective? The purpose of my presentation was very simple. Fundamental and applied research need to go hand in hand, because often we rely on the results coming from you. And if something doesn't sit right in our theories, you can help us find a fix, or the other way around. So I believe that people engaged, practitioners who receive practical good results, need to know the areas of theoretical land survey which will help create modern techniques. Thank you very much once again. After your presentation, I've come to realize that Rakros conference is indeed a scientific conference. And to tell you the truth, I feel an urge to go back to school and start all over. Any questions? No questions. All right, thanks. Thank you very much. And let me also thank all the speakers of this second session. And I wish you all.